Some friends of mine recently reached out and asked for my help. They knew I was studying computer science and thought I would be able to help them with a little problem. They were planning a bank robbery, but they were all terrible drivers. Therefore, they wanted me to use my knowledge of machine learning to work out where in Great Britain they were least likely to get caught if they got into a car accident after robbing a bank. This question also has applications beyond the bank robbing niche, as it will provide rough indication of crash severity and frequency across Great Britain. I began by finding some data. I stumbled across this dataset by Dave Fisher-Hickey that seemed reasonably credible, given it had won third place in the September Kaggle Award in 2017 and was sourced from official police databases. It contains 4 relevant columns: longitude, latitude, police force, and did police officer attend scene of accident. Longitude and latitude are the location of each accident measured in degrees from the Greenwich meridian and equator respectively. Police force stores which police jurisdiction the accident occurred under, and did police officer attend scene of accident contains a boolean, yes or no, that describes if officers were required at the crash site. This dataset turned out to be very clean, with little pre-processing required. There were almost no empty fields, and almost no anomalous values. Additionally, I only needed a few columns from the dataset, so I didn't need to cull as many as I might have had to. The first thing to do was to remove any rows that contained empty values in important columns. Next, I generated a summary of each column to check that their values were as expected and removed any anomalies. Later on, when I ran dbScan, there were a number of outliers which I removed so that they wouldn't form a single giant outline when I ran the convex hull algorithm. Clustering is an unsupervised machine learning technique that aims to group data points into discrete classes. This means that the algorithm starts with a set of unlabeled data points and through some process groups them into classes determined at runtime by the algorithm. dbScan is a clustering algorithm that measures classes by density of data points. When a data point is processed by the dbScan algorithm, all points within a certain distance of it, tuned by the programmer, are added to its cluster. Then those newly added points will be processed and their nearby points will be added to the cluster. When there are no points in the cluster left to process, a new class is created and the next chosen point, chosen randomly, is added to that new class. This continues until no points are left unclustered. Any points that are in a cluster with fewer than a certain number of points, i.e. maybe 5, are considered outliers. Like clustering, classification algorithms also group data points into discrete classes, but they differ from clustering by being supervised. This means that they begin with a set of data points already labelled with their class, and the algorithm then calculates how to class future data points. The k-nearest neighbour algorithm achieves its classification by identifying majority classification of the closest data points to the new data point. The implementation of k-nearest neighbour I used produced a patchwork of coloured areas on the graph. These coloured areas represent which class the majority vote will be in a given area. An alternative classification algorithm is the SVM algorithm. SVM creates its classification criteria by calculating the line between the points of the classes, and then classifies future points based on which side of that line they are. I tried using SVM in this project, but SVM works best when only comparing 2 classes, so it didn't work for this problem. Before applying any machine learning, I plotted all the points by longitude and latitude, along with a series of labels for major cities, to get a sense of what I would be looking at without any complex algorithms. We can immediately observe that the data takes the rough shape of the UK, London is on the Greenwich meridian, i.e. where longitude equals 0, and there are fewer road collisions, accidents implies there was no one to blame, in the north of Scotland. I then used dbScan clustering algorithm to allow the computer to separate the different islands. I used dbScan because I wanted the computer to see each island separately without having to create training data for every single island. I did this clustering so I could create outlines of each island. I did this by drawing convex hulls for each cluster. For the Great Britain cluster, I had to split up the cluster so that it would retain the correct shape. Before I did that, it was just a giant hexagon. I did this all so that I could keep a visual representation of the geography of the British Isles while having less clutter to obscure the results. Finally, I ran the k-nearest neighbour algorithm measuring the density of did police officer attend scene of accident against each police force, and then plotted the results as a mesh behind the outline and the city plots. As we can see, Southeast England is by far the easiest place to get away with car accidents. A prominent candidate for bank robbery in this area would be Eastbourne, because along Terminus Road in Eastbourne sit about half a dozen banks that are all next to each other, meaning my friends can quickly rob them all and then leave in their somewhat treacherous getaway car. Presumably they couldn't afford Jason Statham. There were some limitations with my research. First of all, the dataset only contained data from officially logged police reports. This means I don't have any data on minor incidents, and it is why the probability of police intervention begins around 70%. The dataset is biased towards major incidents and incidents that required police intervention. A second limitation is that the KNN algorithm doesn't know what land and oceans are. This is why the graph around the UK isn't coloured plain white. It's treating the ocean as the same as the land. Thirdly, DBScan also had issues. In return for not needing training data, Northern Scotland with its sparse data got divided up a bit randomly. I did try fixing this by using the k-means algorithm, since I could specify how many islands I wanted beforehand, i.e. how many clusters. But k-means just divided up Great Britain pretty much randomly instead of targeting each island.